Welcome. Today we are solving LeetCode problem number 238, product of array except self. This is a medium difficulty problem. It falls under two topic areas, arrays and prefix sum. Here is what the problem asks. You are given an integer array called nums. You need to return a new array called answer. Each element at index I in the answer array must equal the product of all elements in nums, except the element at index I itself. Now, let's look at the constraints. The array length is at least 2, and at most 10 to the power of 5. Each number in the array is between -30 and +30. The product of any prefix or suffix will always fit in a 32-bit integer. Most importantly, your solution must run in big O of n time, and you are not allowed to use the division operator. That last constraint is what makes this problem interesting. Let's look at some examples next. Let's walk through example 1 to understand what the problem is asking. Our input array is 1, 2, 4, 6. For each position, we need to multiply all elements except the one at that position. For answer at index 0, we skip the value 1 and multiply 2 times 4 times 6. That gives us 48. For answer at index 1, we skip the value 2 and multiply 1 times 4 times 6. That gives us 24. For answer at index 2, we skip the value 4 and multiply 1 times 2 times 6. That gives us 8. For answer at index 3, we skip the value 6 and multiply 1 times 2 times 4. That gives us 6. So our final output array is 48, 24, 8, 6. Simple idea, but we need to do this efficiently, without division, and in linear time. Let's see another example next. Now, let's look at example 2. This one has an important edge case. Our input array is -1, 0, 1, 2, 3. Notice that nums at index 1 is 0. This is the tricky part. Any product that includes this 0 will automatically become 0. Let's go through each position. For answer at index 0, we skip -1 and multiply 0 times 1 times 2 times 3. Since we include the 0, the result is 0. For answer at index 1, we skip the 0 and multiply -1 times 1 times 2 times 3. That gives us -6. For answer at index 2, we skip 1 and multiply -1 times 0 times 2 times 3. We include the 0, so the result is 0. For answer at index 3, we skip 2 and multiply -1 times 0 times 1 times 3. Again, 0 is included, so result is 0. For answer at index 4, we skip 3 and multiply -1 times 0 times 1 times 2. 0 is included, so result is 0. Our final output is 0, -6, 0, 0, 0. Remember, we cannot use division to simplify this. Our algorithm must handle zeros correctly on its own. Let's now look at the brute force approach. Let's talk about the brute force approach. The core idea is simple. For each index I, we loop through the entire array and multiply all elements, except the one at index I. Here are the steps. Step 1. Create a result array of the same size as nums. Fill it with 1s to start. Step 2. Start an outer loop. Iterate over each index I from 0 to end -1. Step 3. Inside the outer loop, start an inner loop. Iterate over each index j from 0 to end -1. Step 4. If j is not equal to I, multiply result at index I by nums at index j. We skip only the current index. Step 5. After both loops finish, return the result array. Let's look at a quick visual. For the array 1, 2, 4, 6, when we compute answer at index 0, we fix I at 0 and skip nums at 0, which is 1. We then multiply nums at index 1, 2, and 3. That's 2 times 4 times 6, giving us 48. We repeat this entire process for every single index. That means for an array of size n, We are doing n times n multiplications. Next, let's look at the code. Now, let's look at the brute force code in Python. We define a function called product accept self that takes the array nums as input. First, we store the length of nums in a variable called n. Then we create a result array called res, filled with ones of size n. Next, we start the outer for loop. For each index I from 0 to n-1, we reset a variable called prod to 1. Inside that outer loop, we run an inner for loop. For each index j from 0 to n-1, we check. If j is not equal to I, we multiply prod by nums at index j. This skips the current element at index I. After the inner loop finishes, we store prod in residential at index I. Once both loops complete, we return the result array res. The key thing to notice here is that we have two nested loops. For each of the n elements, we are doing another full pass of n operations. That gives us a time complexity of big O of n squared. The problem constraint says we must solve this in big O of n. So the brute force will be too slow for large inputs. Let's look at the complexity analysis next. Let's analyze the complexity of the brute force approach. Starting with time complexity. The outer loop runs n times, once for each element. The inner loop also runs n times for each outer iteration. So the total number of operations is n times n, which is n squared. That gives us a time complexity of big O of n squared. To put that in perspective, if n equals 100,000, that's 10 to the power of 10 operations. That's 10 billion multiplications. This will absolutely time out on the LeetCode judge. Now for space complexity. We create a result array of size n to store our answers. We don't use any other data structures. So space complexity is big O of n. This is acceptable since the output array is required by the problem. So the verdict is, the brute force approach is correct but far too slow. The problem explicitly requires big O of n time, and we are at big O of n squared. We need to find a smarter approach that avoids repeating the same multiplications over and over. That's exactly what the optimal approach does. Let's see it next. Now, let's look at the optimal approach. This is where things get really clever. Here is the key insight. For any index I, the answer is simply the product of all elements to the left of I multiplied by the product of all elements to the right of I. Let's see this with our example array. 1, 2, 4, 6. First, we compute prefix products. The prefix at index I is the product of everything to the left of I. At index 0, there's nothing to the left, so prefix is 1. At index 1, only nums at 0 is to the left, so prefix is 1. At index 2, nums at 0 and 1 are to the left, so prefix is 1 times 2 equals 2. At index 3, nums at 0, 1, and 2 are to the left, so prefix is 1 times 2 times 4 equals 8. So our prefix array is 1, 1, 2, 8. Next, we compute suffix products. The suffix at index I is the product of everything to the right of I. At index 0, the right side is 2 times 4 times 6 equals 48. At index 1, the right side is 4 times 6 equals 24. At index 2, the right side is just 6. At index 3, there's nothing to the right, so suffix is 1. So our suffix array is 48, 24, 6, 1. Finally, we multiply prefix times suffix at each index. That gives us 48, 24, 12, 8, which is exactly our answer. And we did it in just 2 passes, no division needed. Let's look at the code next. Here is the optimal Python code. Let's walk through it step by step. We define product accept self and start by creating a result array called res, filled with ones, of the same length as nums. Now we do 2 passes over the array. Pass 1 left to right. We initialize a variable called prefix to 1. Then we loop from left to right. At each index I, we store the current prefix value into residential at index I. This captures the product of everything to the left of I. Then we update prefix by multiplying it with nums at index I, so it grows as we move right. After pass 1, residential holds the prefix products for every index. Pass 2, right to left. We initialize a variable called suffix to 1. Then we loop from right to left, starting at the last index down to 0. At each index I, we multiply residential at index I by the current suffix. This multiplies in the product of everything to the right of I. Then we update suffix by multiplying it with nums at index I. After pass 2, residential holds the final answers. Each element is the product of all elements except itself. We return res. The brilliant part here, we reuse the result array itself to store prefix products, then fold in the suffix on the second pass. We never need any extra arrays. 2 passes, no division, and it handles zeros perfectly. The complexity is big O of n time and big O of 1 extra space. Let's now analyze the complexity of our optimal solution. Starting with time complexity. Pass 1 goes left to right. That's big O of n. Pass 2 goes right to left. That's another big O of n. In total, we do big O of n plus big O of n, which simplifies to big O of n. Now for space complexity. We only use 2 extra variables, prefix and suffix. That's constant space. The result array is required by the problem and doesn't count as extra space. So space complexity is big O of 1. Let's see how we got here from brute force next. Let's connect the brute force approach to the optimal solution and understand exactly how we get from one to the other. In the brute force, for each index I, we loop through all other elements and multiply them together. The problem with this is that we are recomputing the same products over and over again for every single index. That's where the n squared cost comes from. So how do we fix it? We think through 3 steps. Step 1, observe. For each index I, we need the product of all elements except nums at index I. Step 2, split. We realize that all elements except nums at I can be split into 2 parts, everything to the left of I and everything to the right of I. The answer at I is just those 2 parts multiplied together. Step 3, precompute. Instead of computing the left and right products from scratch for every index, we compute them once. We store all left products in one pass. That's our prefix. We store all right products in another pass. That's our suffix. Then each answer is simply prefix times suffix. This eliminates all repeated work. Every product is computed exactly once. The takeaway here is powerful. Whenever you notice repeated computation in a brute force approach, think about whether you can precompute and reuse. This pattern shows up in many big O of n optimizations. Let's finish with the comparison table. Let's wrap up with a full comparison of the 2 approaches. Looking at time complexity, brute force is big O of n squared, while the optimal is big O of n. A massive difference for large inputs. Space complexity. Both use big O of n for the output array, but the optimal uses only big O of 1 extra space since we only track 2 variables, prefix and suffix. Neither approach uses the division operator. Both handle zeros correctly. In terms of loops, brute force uses 2 nested loops, while optimal uses 2 separate single passes. And for the LeetCode result, brute force will get a time limit exceeded error on large inputs. The optimal solution gets accepted. Here is the key interview tip to remember. Always start by writing the brute force solution first. It helps you deeply understand the problem. Then look for repeated work. Where are you computing the same thing multiple times? Once you spot it, ask yourself, can I precompute this once and reuse it? For this problem, the repeated work was recomputing left and right products for each index. The fix was to separate them into a prefix pass and a suffix pass. That's it for LeetCode 238, product of array except self. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.